The goal of this section would be for us to use the exponent properties from section 5.1 last chapter and apply them to rational exponents, which yesterday we said rational exponents meant fractional exponents or fractions. So instead of our exponents being like -2, +5, -4, which were integers, now our exponents are going to be fractions. So taking what we know from section 5.1 and kind of applying it to this section to pull them together. So underneath, these are the properties that we talked about in 5.1. So you should hopefully be able to fill out the property side pretty easily. Next to it is an example with a rational exponent instead of an example with an integer exponent like we did in section 5.1. So the first one, we have a to the m times a to the n. So Paige, when you have that property where the bases are the same, what do you do with the exponents?
You add them.
Yeah, you add them together. So m plus n. So if you look at the example, we have 4 to the 1/2 times 4 to the 3/2. So really we're adding 1/2 and 3/2 together. So Paige, if you add 1/2 and 3/2, you get?
4
So 4/2. Yep.
Oh yeah.
So you add the top, the denominator stays the same. When you have common denominators, you're adding the top number, but the base stays the same, that bottom number. Paige, what is really 4/2?
1/2. Oh, 2.
2.
Oh, sorry.
That's right. And 4 squared is?
Oh, 16.
16.
Sorry.
Nope, you're good. I just wasn't done. So you actually get a nice answer of 16 there by adding the exponents, reducing the fraction, and then squaring the 4. So you get 16. The second one, we have a to the m, and then the n is outside. So what did that property say to do with the exponents? Ethan?
Multiply.
Yeah, multiply them. So m times n. That means, Ethan, we have 2, and then we're taking 5/2 times 2, which I'm really going to write 2 over 1, so that we've got a fraction times a fraction. What's that make, Ethan?
5.
Yeah, that makes 5, because you have 5 times 2, which is 10, divided by 2, so that becomes 2 to the 5th. Do you know what 2 to the 5th is?
32.
Awesome, 32. So that one's 32. Let's see, property 3, where you've got a quantity inside, the exponent outside, remember, distributes through when you're multiplying the numbers inside. So this would not be the same if it said a plus b. That guy doesn't multiply. This is just a times b. So you just distribute your exponents to the variables inside. So a to the m times b to the m. If I had 15 in there, I'd just distribute it to all 15 pieces, as long as they're all being multiplied. So it only refers to multiplication. So underneath here, that means we would have 16 to the 1/2 times 4 to the 1/2. Now there's a couple of different ways you could think about this to try and simplify it. What's one thing that you could do to simplify 16 to the 1/2 and 4 to the 1/2, Sarah?
Square root of the first.
Yep, so we could square root the first one, we could square root the second one. And what would that make then, Sarah?
4.
Yeah, so that makes 4 times 2, which is 8. What else could you have thought about doing? Virginia? Right, because the powers are the same, you can also multiply those together to get 64 to the 1/2, which is still 8. So remember, the power of 1/2 means square root. So either way, you're going to get the same answer. It just depends on what you kind of recognize first. But if they have the same power, you can multiply them together, because now we're just dealing with the square root of 64, which is really what we could have done down here too. After we put them in square root form, we could have multiplied those together. Questions with the first 3 properties? So property number 4, Ryan, says a to the negative m. What do you do with the negative exponent? Yep, so put it on the bottom under 1 to make it positive. So 25 to the negative 1/2, Ryan, would be?
1 over the square root of 25.
Good, so 1 over the square root of 25, which is?
1/5.
1/5, awesome. So it would be 1 over 25 to the positive 1/2, but a square root is a 1/2 exponent. The last two are our division or fractional problems here. So we have a to the m divided by a to the n. Is it what happens with the exponents when you're dividing?
You like add or subtract them, so it would be a m minus m.
Yep. So over here is if we're subtracting 5 halves minus 1 half, we end up getting
4 halves, which is 2.
good. And 3 squared is
9.
awesome. So the last one, this is that same distributive property, but now we're dividing. You just kind of bump that m to both powers. So a to the m divided by b to the m. So that means we have 27 to the 1/3 and 8 to the 1/3. So Kate, what would you do with 27 to the 1/3?
Cube root.
Yeah, so remember 1/3 really means cube root. And what is the cube root of 27, Kate? 3. And the cube root of 8 is? 2. So you get 3 halves. Any questions with those properties? So the properties are pretty straightforward. However, the problems get a lot more interesting when the exponents aren't necessarily the same denominator. So if you look underneath, it says to use the properties of rational exponents to simplify the expression. So our goal is to get it broken down as far as it'll break down using the properties of exponents. We have for letter A, 9 to the 1/2 times 9 to the 3/4. So the bases are the same. We know that we can add those exponents together. So we've got 1/2 plus 3/4. Sam, how do you really add fractions if the denominator isn't the same?
You have to give them the same denominator.
Yeah, we have to get a common denominator. What would the common denominator be?
4.
So it would be a 4. So that means the 1/2 becomes
2/4.
So, 2/4 plus 3/4 is
5/4.
5/4. Okay, so here's where it changes a little bit. So we added 2/4 plus 3/4 because common denominator says I would multiply both of those by 2 to get a denominator of 4. 2 plus 3 is 5, that's the top, and then over 4. This can be simplified. So you can't just leave it as 9 to the 5/4 if we can try and break it down a little further. So if you look at the fraction 5/4, usually I tell you to keep fractions as improper fractions. However, we want to try and simplify this. Sam, do you know what 5/4 would be as a mixed number? So what would 5/4 be, Isabel, as a mixed number? 1 and 1/4.
Oh, I forgot.
That's all right. Maybe I just didn't use the right terms for you. So I could write that as 9 to the 1 and 1/4. That 9 to the first can be pulled separately. And then I can separate that also with the 1/4. So that would become 9 to the first and 9 to the 1/4. So that my fraction is no longer an improper fraction. I now just have 9 times 9 to the 1/4. This is simplified because we broke it down. My 5/4 could break that 9 to the 5/4. That could be broken down so that we have a smaller exponent. So making that an improper, or taking it from an improper fraction, making it a mixed number, I now have just the 9 and then the 9 with the 1/4. Questions with that? 'Cause that's a little weird. Kate?
So why couldn't you? Remember the square root thing where like you take the root of the denominator and raise the whole parentheses to the
We could,
numerator?
you
Why
could,
couldn't
you can do that exact same thing, and then you would break it down the exact same way. So you're saying right here, so we'd have the 4th root of 9 to the 5th. That's what you're talking about, right? So then you could also break it down using 9 to the 5th, but you'd have to actually calculate 9 to the 5th.
Okay.
And it's 59 something, 59,049 maybe. Yeah, it's a big number. So trying to get a huge number like that to break down is harder than trying to think of it as a mixed number to separate it and break it down. But it still works the same way. It's still the same thought process. Other questions, Jenna? Why don't we multiply the 9s? That's a good question. So why don't we multiply those 9s together?
It's 9 to the 1/4 is typically no longer 9.
Yeah, because 9 to the 1/4 is really the 4th root of 9. So they're not the same 9 because that one has an exponent, the other one doesn't. So we can't multiply those together because this is really a whole number and 9 to the 1/4 is a decimal value. Good question though, 2 good questions. Other questions? So these mean the same thing, we're just keeping the fractional exponent. Ethan?
Never mind. Wait, do you have to put it like with the square root thing?
No,
Not
do
square
not.
root.
4th root, I know what you're, no, you do not. H.
Does it matter how you write it since they mean the same thing?
It does not matter, no. The book will have it in exponential form. So if you have yours as a 4th root, then you just kind of have to remember that it matches the same answer. Unless it said to like leave your answers with rational exponents. Other questions? Alright, so if you look at letter B, I'm going to try and work through this one as well. We have 7 to the 2/3 times 5 to the 1/6. All of that's cubed. So when you have a power outside, that power is supposed to distribute to the exponents inside. So that means we have 7, bless you, to the 2/3. I'm just writing this to try and get you to see like they're actually being multiplied together. So 7 to the 2/3 times 3. I'm writing it as 3 over 1. We also have 5 to the 1/6 times 3, or 3 over 1. So when you multiply 2/3 times 3, does anybody know what that exponent becomes? Okay, 2. And then 5 1/6 times 3 over 1, Kate, is 1/2, because that's really 3/6 or 1/2. So 7 squared can change to 49. 5 to the 1/2, I can't multiply 49 times 5 because again, this is really the square root of 5. And that's 49, so they're different types of numbers. So you can leave it like that, or if you'd like if you'd rather see the square root in it, you could write 49 square roots of 5. They mean the exact same thing. Questions? So see if you can try letter C. We have 3 to the 5/6 divided by 3 to the 1/3. So dividing means you need to subtract the exponents. Get those exponents to subtract. And then after that, we see if it can be simplified any further. So get a common denominator, subtract those fractions. So Virginia, what would your common denominator be?
6.
So it would be 5/6 minus 2/6, which makes 3 to the 1/2. So 3 to the 1/2, square root of 3. Letter D, we have 16 to the 2/3 divided by 4 to the 2/3, and then all of that's to the 4th power. So what would you do with letter D? H?
Could you do, never mind, that's exactly what I was going
Ethan?
You would do the inside the parentheses first.
Okay, what would you do inside the parentheses?
I would. Subtract. No, you wouldn't subtract.
No, you're good though. Like, what do you do inside these parentheses? They both have the same power, so they're the same types of numbers.
So just divide 16 by 4.
Right, divide 16 by 4. If the powers are the same, then they're the same type of number. They're both to the 2/3. So you can divide 16 by 4, and Ethan, 16 divided by 4 is 4. it still has the power of 2/3. And then we have a 4 outside. So you can still do that, like it's still the same property. So Ethan, when you multiply 4 times 2/3, what does that give you?
8/3.
Right, so we have 4 to the 8/3. Okay, so this one now goes back to like number 1. This is an improper fraction. So what is 8/3 as a mixed number? Sam?
2 and 2/3.
2 and 2/3. So that means I have 4 squared and 4 to the 2/3. Sam, 4 squared becomes
16.
16. Questions?
Wait, so then the answer is 16.
16 times 4 to the 2/3. 8.
So in the first step, when you divided the 16 and 4,
Yes.
why did the 2/3 stay? Because isn't that like attached to it, like
So,
divide out?
If we wrote that as a rational, so we have the cube root of 16 squared, and we'd have the cube root of 4 squared. So because these are exactly the same, you can write them, and we're going to do this property right on the next page. You can write them underneath one fraction. But like that property is on the next page of your packet. But because they're like exactly the same, the property says that you can take the radical and write them as one fraction, or you could separate the radical and look at them as 2 separate fractions. Other questions? So if you flip the next page, what Kate was just asking about are the 2 properties on the next page. So these are, like what we just dealt with, those were properties of rational exponents. So properties of exponents, that's what we were working with. But there are also properties of square roots or radicals that we talked about before as well. And those properties say if I'm multiplying square roots or radicals together, you can split them apart into their own separate radicals. So instead of just having a square root, we can have an nth root. So I can take the nth root of A times the nth root of B. Or I can combine them together to go back into the same nth root. So like when we did the square root of 20, we broke down the square root of 20 into what 2 numbers? How would the square root of 20 break down? 8? 5 and 4. So it would be the square root of 4, square root of 5. So 2 square roots of 5. Well, this property says you can do that with any root. It doesn't just have to be a square root. But you're allowed to break them down. Or I could combine them together if they have the same exponent as well. So here's the division property. So if I'm dividing 2 things with the same root, you can separate them into their own separate roots. Or if you have separate roots, you can combine them together if that helps you solve the problem. So they're like, but you can go back and forth. It's not just always having a fraction and separating it. If I have 2 separate pieces, we can combine them together to simplify. And I'll show you what that looks like in one of the problems underneath. Any questions with these properties? So underneath with example 2, it says use the properties of radicals to simplify the expression. So this first property says the 5th root of 27 times the 5th root of 9. That's this property here. Right now we have them separate. But what the property says is that if they're the same root, you can multiply them together to pull them back to try and simplify it as well. So because they're both 5th roots, they're the same type of value. So I could really write this as 27 times 9 under the same radical. Now you don't have to, but that's what the property is really saying that you're allowed to do. Does anybody know what 27 times 9 is, Ethan?
243.
243. So on your radical sheet, is there a 5th root of 243? So Ethan, is there in the column of powers of 5, is there 243?
Yes.
And it is
3.
3. The 5th root is odd, so I don't need a plus or minus, and we just have that 243. Was positive, my answer is positive. So with letter B, we have the cube root of 192 divided by the cube root of 3. Right now, by themselves, you can't really do anything with them, But if you apply the property, we could take 192 divided by 3, but it's still under the same cube root by the property. So Sarah, 192 divided by 3 is 64. And then the cube root of 64 is 4. So that property says that if the roots are the same, then you can combine them together or you can separate them, depending on what the problem's asking you to do. Questions? So why don't you try the 2 underneath? I think there's 2 checkpoint problems. So the first one says 6 to the 6 times 5 to the 6th. And then that's to the negative 1/6. And then the second one, the square root of 245 divided by the square root of 5. So there's 2 different ways you could approach number 1. Kind of just depends what you see, what you're thinking about. But there are 2 different ways to approach the problem to start. Aaron, how'd you start number 1?
I distributed the negative 1/6 to the
Okay, so that gives you then 6 to the
negative first.
negative 1 and 5 to the negative 1. Then what'd you do?
Then I put them under 1.
So we have 1/6 and 1/5, which becomes
1 over 30.
1 over 30. Did anybody solve it differently? Tyler, how'd you do it?
I did 6 to the 6 times 5 to the 6.
So because these have the same powers, you can multiply them together and get
30 to the 6.
30 to the 6th. And then Tyler, what'd you do?
I multiplied the 6 times the exponents and I got 30 to the negative first. And
Which is,
I had just flipped it down.
yeah, still the same thing. So it kind of depends what you see. But if the bases are the same, the powers are the same, the exponents are the same, you're allowed to multiply those bases together. You get the same answer. It just depends on how you approach the problem. Number 2, we have the square root of 245 divided by the square root of 5. Ethan?
I put the square root around 245 over 5.
Yeah, so the entire square root, because they're both square roots, and then when you divide, you get,
49.
what is the square root of 45? How could you break that down?
49.
49. Sorry, what's the square root of 49?
7.
7. Good. Questions? Yeah, there's multiple ways. Did you rationalize it? Top and bottom? Yeah. All right, so I want to do 2 more problems at the bottom of the page. We'll look at A and B here. If something's in simplest form, that means whatever's underneath the square root, and I'm just going to say the nth root of A, cannot be broken down any further. That means there's not a perfect square or a perfect root left in the problem. So this number right here, you can't break down into like the square root of 4 and the square root of 5 if I was dealing with the square root of 20. That's when something's in simplest form. So it's all the way broken down, you can't break it down any more than it is. So if you look at A and B here, we have the cube root of 135 and the 5th root of 128. So we're always used to thinking of square roots getting broken down, but you can break down any root. It doesn't just have to be a square root by using the same process. Except you need to go into your chart and look at the cube column instead of the square column. So in your chart, looking at those powers that are cubed, what number goes into 135 that's in the cube column? Tyler? 27 times what, Tyler?
5.
5. So you're picking 27 because 27 is a perfect cube. Tyler, 27 becomes 3, and then we have the cube root of 5. So it works the same way as square roots, but now you have to look at the right column, which is why that sheet is so helpful, so that you know like what numbers apply to the problem you're working on. So with letter B, we have the fifth root of 128. So go to the column that has all the powers of 5. So which one of those numbers would go into 128? Sarah? 32. 32 times what? So the exponent, or the power, tells you the column to look at. And then you're picking a number from that column. Not any old random number. It has to be one from the power of 5 columns. So the fifth root of 32 is 2, and then we have the fifth root of 4. So we'll stop there. We'll look at rationalizing maybe tomorrow. Are there questions? So in your book, it's 3 to 31 odd. Please do the odds. I think I omitted the word odd on the assignment sheet, and if you'd like to do all of them, go for it. But you could do the odds as well. So 3 to 31 odd. And then I'm looking for 2 more people to look at 21 and 27.
Does that count for the next semester?
No, for this semester. I still have people for this semester.
Would I get 1 point if I didn't?
No, because I have other people that still need to do them. So, Aaron, I think yesterday I told you I'd get you today, right?
Today did not have to do with it.
You have 2 in. Never mind. Aaron has 2. Oh, I remember you getting that other one. Let's see here. Caitlin's not here. Ethan just left.
This came out super easy.
No, there's a lot.
You said you had 2 already.
Alyssa, would you like to try 21? Sure.
Oh wait, one more.
Just
Did you write it down? Oh.
Do you need this note card?
I'll take it. Yeah,
Here's one more
thanks.
weird question. Oh yeah. What city did you
Hey,
live in?
Timmy, do you think you could do 27?
Moscow.
Try it out.
Okay. Have a good day.
Thanks, you too.
That was good.
Thanks, you too. See you, Virginia, you as well.